All right, everybody. Good evening. Thank you so much for joining us. For those, there's a couple of new folks on here. I'm Beth Maffey. I'm one of the program managers with the Center for Professional Personnel Development. And tonight we have Dr. Berghage and Dr. Elsa Sanchez with us. They're going to be talking to you about aquaponics and hydroponics, getting us all prepped for our PD Friday and Saturday. There's a number of things that John put in his email to you. If you didn't receive that email, well, you probably did because you're here. But if you didn't, please let me know in the chat as we move forward. Also, at the end of this session, I'm going to just kind of review that email to make sure we're all on the same page in case you have any questions. But to, again, be conscious of everyone's time, we're going to turn this over to Dr. Berghage and Dr. Sanchez. And I'm super excited to have you all with us.
Okay, excellent. So this evening, what we're going to do is a little bit of background information. We're going to talk about plant nutrition at a basic level, and water quality at a basic level in terms of hydroponics operations, with the idea of sort of laying some groundwork for what we're going to be doing on Saturday, which is going to be mostly hands-on stuff out in the greenhouse, working with our hydroponic systems and our aquaponic systems. So I'm going to start out here, and I'm going to share my screen in a minute here if I can get it to work. Okay.
Does it look like it's letting you?
It's being kind of funky here right now. All right, let's see if this will work. Okay, that looks better. They, for some reason, the preferences had it locked out. Okay, so what we're going to talk about first is we're going to talk about hydroponics nutrition. So get up to the beginning of this slide set. And as a sort of background information, what we're going to do is cover some basic nutrition, plant nutrition. If anybody has any questions as we're going along, feel free to unmute and just speak up, or if you type in the chat box, maybe Bethany, you can keep track of the chat box. If anybody types in there, you can let us know. Okay, good. So from a nutritional standpoint of plants, there's a number of things that we have to provide the plants. And when we're doing hydroponics or aquaponics, obviously all of them have to come from the nutrient solution that we are providing to those plants. So we have to provide carbon, hydrogen, and oxygen, nitrogen, phosphorus, and potassium, sulfur, calcium, magnesium, and then some minor nutrients: iron, manganese, zinc, copper, boron, and molybdenum. Also, chlorine and nickel are actually required, but they're required in such small amounts that we can ignore them. There's more than enough environmental contamination to account for those nutrients. So next thing, so we're going to cover each one of those in turn in terms of thinking about the nutrients and how the plant takes it up. But I want to just basically back up real quick and remind everybody of sort of basic biology, basic botany, how plants take up nutrients. So there are two basic pathways that the nutrients that we're providing in our hydroponic solution are getting into the plant. One is passive through the transpiration stream, and the other is active. So at the root tip, it's not suberized, and the nutrients can just move up through the water stream up into the plant. The active uptake occurs further back in the root typically, and is a measure of acidifying the environment to make the nutrients more available and then having to move them across membranes. So we have to think about both of those transport mechanisms when we're thinking about managing the plants from a hydroponic standpoint. So what we're going to do here is kind of go through the essential nutrients one at a time, or small groups at a time, and discuss how much is required of each in the plant, because obviously we have to provide all of that. And then we're going to talk a little bit about where it's coming from. And then after I get done with this, Elsa's going to come on and talk to us about water quality and how that also affects nutrient availability, and how you make a nutrient solution, and how much of these nutrients is in, say, a Hoagland solution, which is a common nutrient solution. So carbon, hydrogen, and oxygen make up about 90% of the dry weight of a plant. They are components of organic matters, organic compounds, and they're obtained from CO2 and H2O. And while you might not think about it routinely, we can have deficiencies of both of these things based on not having enough CO2 in our greenhouse, or obviously not having enough water. So CO2 deficiency usually is going to occur in the winter when the greenhouse is closed up and we maybe have some lights on, or the sun comes up in the morning and there's no gas exchange with outdoors. The plants can use that CO2 very quickly, draw it down to the compensation point where there's no more growth occurring. And unless we supplement that CO2 or we ventilate the greenhouse, we're going to basically stop that growth process at that point. And then H2O, of course, we have issues with too, potentially. So normally you don't see a CO2 deficiency in a hydroponic operation, but you can. And it certainly can limit the growth of plants during certain seasons, which is why a lot of commercial operators or commercial producers will inject CO2 into the greenhouse, especially during the winter months, to increase the plant growth. So nitrogen is required around 2 to 4% or so of the dry weight of the plant. So it's a pretty substantial component of the plant. It is a component of amino acids, proteins, coenzymes, nucleic acids, and it's obtained from nitrate and ammonium. So the plant can take up either one of these two forms. And there's a little bit of a difference between them in terms of the way the plant handles both of those and how it manages it, right? So ammonium is actually toxic to plants. That toxicity occurs generally in low light, low temperature, and saturated low oxygen conditions. And it occurs because the plant has to, when it takes up ammonium, it has to utilize that ammonium immediately. It can't store it in the vacuole of the cells. Nitrate, on the other hand, can be stored in the vacuole of the cells, and so the plant can basically handle as much nitrate as we want to give it. But ammonium has to be attached to a carbon skeleton, turned into an amino acid. Otherwise, we're going to see ammonium toxicity. We see this often with seedlings and other plants, and what this means to us from a standpoint of managing our hydroponic solution in the system is that during low light, low temperature times of the year, which is kind of what we're getting into right now, we need to back off on the amount of ammonium that we're providing the plants relative to the amount of nitrate. So this time of year, typically you're going to want to switch your nutrient solutions away from high ammonium fertilizers and into high nitrate fertilizers to prevent ammonium toxicity. So in the environment, typically what happens is ammonium in the soil anyway is converted to nitrite and then nitrate in a field soil. That requires oxygen, which is kind of why that happens when we don't have enough oxygen present in the soil, when we have saturated conditions. We're not getting this reaction to occur. This is a microbial process mediated by microbes. And it's also actually really bad if we get stuck in this middle process with nitrite in the soils. So I know you probably have all seen, low spots in cornfields in the early spring where the water accumulates, where they've applied ammonium fertilizer and the corn plants turn yellow and get stunted. That's typically a nitrite toxicity. And we can do that in our hydroponic solution as well if we don't have good removal of the nitrate or the ammonium to nitrate based on not having enough oxygen present. So nitrate is toxic to plants as well. Generally occurs in those saturated low oxygen environments. So normally what we want to do is switch. And the typical amount that we're going to switch, so in the summer months, we can have maybe 50% of our nitrogen coming from ammoniacal nitrogen and not have any problem with that, or even more. In the winter months, normally you're going to want to switch down to maybe 12.5 to certainly no more than about 20 to 25% ammoniacal nitrogen in the system in order to make that work. So sulfur is about 5.5% of the dry weight of plants. It's a component of amino acids, proteins, coenzymes, other things like that, and it's obtained from sulfate. Now, we have to provide this in our hydroponic solution, but typically we don't worry about it when we're mixing up hydroponic nutrient solutions. And the reason we don't worry about it too much is because sulfur is an anion, and it acts as a carrier in most of our fertilizers for a lot of the cations that we use. So, for example, the magnesium, when we're meeting on Saturday and we're actually mixing up nutrient solutions, we're going to be obtaining our magnesium from magnesium sulfate. We can obtain calcium from calcium sulfate. Sulfate is a carrier for lots of other things. So typically we get more than enough sulfur in our fertilizer solutions so that we don't really actually need to add any additional sulfur to the solution. There are times, though, depending on the solution that you're working with, and especially if you're trying to show your class, your students nutrient deficiencies, where you might not add enough sulfur, and you might actually deliberately cause that problem. So phosphorus, about the same amount as sulfur, about 0.4% of the total plant dry weight ends up being phosphorus. It's a component of ATP and NADP, and it's an intermediate of metabolism, and membrane phospholipids are required, nucleic acids. It's obtained from HPO4 and HPO4 minus 2. So phosphorus availability is very highly dependent on the pH of our media solution. So if we get particularly acid, we're going to switch to a form of phosphorus that's not as available. And if we get particularly basic, we're going to have less availability of phosphorus as well. So that's normally why we want to stay somewhere in that kind of neutral range with our pH for our nutrient solutions to maximize the availability of phosphorus in the solution. And the availability of phosphorus to the plant. So another essential nutrient, potassium, that's about 2%. So that's back up to sort of back in the range of nitrogen. So about 2% of the dry weight. It's essential for enzyme activation, turgor, and osmotic regulation. So in your body, we use sodium. In our bodies, we use sodium to osmoregulate. In the plants, typically that's going to be potassium that is used for osmoregulation. It's really important from a standpoint, especially if you grow cut flowers, it's really important from a standpoint of managing cut flower production in your hydroponic system. Because if I grow a cut flower that is deficient in potassium, and then I cut it and put it in a vase of water or whatever, it's going to wilt a lot more than one that has sufficient potassium because it doesn't have the osmotic regulation. So potassium is obtained from K+. So it's a cation, and we're typically going to be using in our nutrient solution something like potassium nitrate to provide that, or also maybe some KH2PO4, potassium phosphate monobasic. Both of those are pretty common fertilizer sources. We'll be working with both of those on Saturday when we're in our actual workshop session. Calcium, about 1.5% of the total dry weight of the plant is calcium. It's essential for enzyme activity, signal transduction, and cell structure. It's kind of, you can kind of consider it as part of the glue that helps hold plants together. So anybody who's ever grown poinsettias as one of the crops that you grow in your greenhouse with your students knows that those plants are very prone to having the branches fall off from them. That's a calcium issue. And if you increase the amount of calcium in that plant, the branches won't break off and fall off as often because it's a cell structure thing. It's very, very tightly regulated in the plant because of that signal transduction thing. So it plays a role in a lot of hormonal responses and responses to light and responses to other signals. And so it's very, very tightly regulated in the plant. The plant keeps the level in the cytoplasm very, very low so that it can work this way. It's obtained from calcium. And normally we're going to be getting most of our calcium from calcium nitrate. Although there may be some situations where you don't want that much nitrogen and you're going to get your calcium from calcium sulfate. So magnesium is required at about 0.4% of the total dry weight of the plant. It's also essential for enzyme activation and phosphotransphorases. It's also a component of chlorophyll. So the plants can't photosynthesize properly if we don't have enough magnesium. So we need to provide enough magnesium. Normally that's going to come from magnesium sulfate. The available form of magnesium to the plant is Mg2+, so it's a cation, just like are the other ones. So the minor nutrients that we talk about are micronutrients. It's kind of a misnomer to call them minor nutrients because they're not really minor. They're extremely important, actually. And micro maybe because they're not required in very high concentrations, but they are required. And if we don't provide them in our nutrient solution, depending on what our background water supply is, you're going to see nutrient deficiency symptoms. So the ones that we see most commonly in our operations here on campus, we'll see manganese deficiency sometimes. And we'll also see iron deficiency. Iron deficiency very commonly because there's not enough iron in many of the fertilizer solutions. And we have typically a fairly high pH water, and we're coming from a calcareous aquifer, so there's lots of calcium and magnesium because we're pumping water from a limestone aquifer, which means that iron becomes less available. So we see iron deficiencies fairly frequently as well. So manganese is about 0.02% of the dry weight. So it's not very much. We don't need to provide very much of it, but it is essential. And if we don't have it, it's going to mess with all sorts of systems that are related to enzyme activation and for water splitting, which is essential for photosynthesis to happen. So iron about the same amount, about 0.02% of the dry weight, can be a little bit more, can be a little bit less. Also functions kind of the same way in terms of controlling redox potential changes, and it's essential for photosynthesis and respiration because of those redox changes. So kind of back to what we talked about a minute ago with thinking about phosphorus, where we're thinking about energy transfer within the plant. Iron is critical for that energy transfer within the plant. And if I don't have it, I'm going to see chlorosis of the tissue. I'm going to see potentially necrosis, and I'm definitely going to see stunting of the growth of the plant. So molybdenum, 0.0002% of the dry weight. Minuscule amount of molybdenum is required. So we typically don't have to add it to our solutions. There's probably enough, depending on how you're managing your hydroponics, in the background water or in contamination from other sources, but occasionally you will see deficiencies of it. It's essential for redox changes and nitrate reduction, so it's critical to the plant, and it is an anion, so it doesn't exist on the cation exchange capacity in our greenhouse media if we're doing soilless media cultures, which again, we'll talk more about that on Saturday. Copper, about 0.002% of the dry weight. So again, very, very small concentration, essential for redox changes and plays a role in photosynthesis and respiration. That's obtained from Cu2+. A lot of these nutrients, the minor nutrients, copper, manganese, iron, We can obtain them either from sulfates or we can obtain them from chelated nutrients. And so a lot of times with the iron especially, we'll use a chelated nutrient. With some of these others, we'll use sulfates. And that'll become important, and we'll clarify that too on Saturday in terms of thinking about what source you're going to use and why you're going to pick that individual source. So zinc, about 0.003% of the total dry weight. It's an enzyme cofactor. It activates enzymes. It's obtained from ZN2+. So again, very small concentrations. It's not uncommon to have enough zinc in your water supply, depending on what kind of pipes you're running your water through. Same thing with copper. It's not uncommon especially if you have copper pipes, to have more than enough copper in your water supply to supply the copper that's required for your hydroponic system without adding any additional nutrients to that. Boron, about 0.006% of the dry weight, necessary for enzyme activity, cell division. It's obtained from borate, so it's a anion. There's a number of different sources. I can use boric acid to provide this. You can also you can just go down to the grocery store and buy laundry detergent, the borax laundry detergent, which works just as well. So borax is a great source of boron for your hydroponic nutrient solution. And that's what we're going to use on Saturday when we put boron into our nutrient solutions. We're going to actually use borax. Chlorine, very vanishingly small amounts of chlorine are required, but it does play a role in water splitting, and it's obtained from chlorine, and there's more than enough usually in the environment. Some plants also use sodium, 0.2 to maybe 5% of the dry weight. It plays a role in turgor pressure for some plants. It's obtained from Na+. In most plants, sodium is not required, and in fact, it actually ends up being a problem in many of our hydroponic solutions when we have too much sodium, especially if we have too much sodium relative to calcium and magnesium. And Elsa will talk about that in a little bit when she's talking about water quality. She'll talk a little bit about the sodium absorption ratio. So a few other things that we need to think about in terms of nutritional requirements is pH. So pH is and acidity. So pH is an intensity measure. It expresses the existing concentration or activity of hydrogen ions. And the reason we care about it is because many of these nutrients availability in the system is a function of pH. So we typically try to stay somewhere near this neutral zone where we have maximum availability of phosphorus. You can see the availability goes down dramatically when we start to get alkaline and goes down dramatically when we begin to get into an acidic environment. Some others, like iron, is restricted in availability when we become more alkaline, when we raise the pH, and becomes much, much more available when the pH is lower. And we can actually see toxicity symptoms at the lower pHs. So normally, when you mix up a hydroponic solution or we're growing in some kind of a soilless culture mix, we're going to want to stay somewhere between 6.5 and maybe 7.5 in terms of pH in order to maximize the availability of nutrients to our plants, our crops. So there's a few other things to think about, again, kind of as background material for what is happening when we mix up a nutrient solution. So there are some common antagonisms and interactions between certain nutrients. So if I have nitrogen and potassium in the solution, which obviously I need to because they're both essential nutrients. If I have too much nitrogen, I can affect the availability of potassium. If I have too much potassium, I can affect nitrogen metabolism within the plant. That becomes real important. So on Saturday, we'll be looking at and working with some tomato crops in the greenhouse. That becomes really important with tomato plants when we're fruiting a tomato plant, because they have a much higher potassium to nitrogen ratio when they're fruiting than when they're growing vegetatively. And so we want to have that ratio, kick it up to maybe at least 2 to 1, maybe 3 to 1, or I know some growers who kick it all the way up to maybe 4 or 5 to 1 with potassium to nitrogen to avoid collaring on the tomatoes. Another real common antagonism is phosphorus and zinc. So too high of a level of phosphorus can restrict the availability of zinc. This is more common in a field soil than it is in a hydroponic system, but you can see this as an issue sometimes in a hydroponic solution as well. Potassium can affect the availability of and activity of nitrogen, calcium, and magnesium. They're all cations, right? And so especially during that active uptake process, they can interfere with each other. Sodium can also affect the availability and uptake of other ions. So if I have a lot of sodium in the solution, I can affect the availability of potassium, calcium, and magnesium. And that's why that SAR, the sodium absorption ratio, becomes important. Calcium affects magnesium. So we typically want a relationship between calcium and magnesium where we have more calcium than magnesium, but not much more than maybe a 2-to-1 ratio on that. If I get up to 3 or 4-to-1 calcium to magnesium, I can start negatively affecting the availability of magnesium and possibly even induce a magnesium deficiency. I can also affect boron availability by having too much calcium, or the activity of boron anyway. Magnesium affects calcium. Iron and manganese both affect each other as well. So I want a ratio between iron and manganese that is typically more iron than manganese, maybe 1-to-1 to 2-to-1 in terms of that ratio. If I get my ratio way out of balance, so I have a lot of iron, I can induce a manganese deficiency. Or if I have a lot of manganese, I can induce an iron deficiency. They both look kind of similar sometimes in the plant. And so it's sometimes very difficult to tell what you've created when you have created one of those or the other of those in terms of a deficiency symptom. So a few other things that affect nutrient availability to plants. The redox or oxidation reduction state of the solution that we're using, or the soil that we're growing in, or the potting soil, or the gravel, or whatever it is that we're using, the rock wool, affects the redox state and affects the amount of soluble manganese and iron. So if I get into a oxygen stressed environment, I can, especially with manganese, increase the availability of manganese to the point where it can become toxic. And the same thing with iron. I can make iron more toxic to the plant by reducing the system, but basically changing the redox potential. Okay, so that being a sort of starting background, what I want to do now for maybe the next maybe 15 to 20 minutes is look at some common nutritional problems that you're going to see in your hydroponics or your aquaponics systems, and talk a little bit about diagnosing each one of these things. So one real common problem is soluble salts damage, and that happens especially when I'm working with a nutrient reservoir that I'm refilling regularly and not monitoring the EC on regularly. I can increase the salt level to the point where it can become problematic for certain plants. So it can be caused by over-fertilization, poor water quality. If I have a lot of sodium in my water, the plant doesn't really need a lot of sodium. It doesn't take up a lot of sodium. And so that sodium ends up being left behind, and that can increase the soluble salts and damage the plant from the ability of the plant to take up other nutrients over time. So in a soilless production system, that can also occur from inadequate leaching. So if I'm running an open soilless media production system, so say an open bag culture system, and I don't leach it enough, what I'll end up doing is build up the salts in that system, and it'll cause problems. So the symptoms from soluble salt damage, and it's much more problematic really with young plants than it is with old plants. So we really see this problem much more frequently with seedlings in our production systems. Once the plants are well established, they can tolerate much higher salts, but with seedlings, you can burn a seedling really easily with too much salt. So wilting, dark green foliage, dead and burned leaf margins, and especially leaf tips. That makes sense when you start thinking about where the transpiration stream ends, right? So if the plant is taking up too much salt, it's going to move through the transpiration stream, and where the transpiration stream, and it's going to use what it wants to, what's left over is going to end up at the end of the transpiration stream, which is going to be the tips of the leaves. And that's why you get tip burn. You can also see leaf cupping and root death from too high soluble salts. So we're going to monitor that by monitoring the EC. So we're going to be doing a bunch of this on Saturday as well in the workshop on Saturday. We're going to work with some EC meters, and we're going to measure and monitor EC in some of our nutrient solutions. So the cure for too high soluble salts is to leach with clear water and reduce the salt level. So I want to bring it down. If I'm working with a nutrient reservoir and I end up with, say, a EC of 3 or 4 or 5 over time, I need to drain that out and rinse it out and start over with a new fresh nutrient solution, because otherwise I'm going to end up with problems. We see that also sometimes in our aquaponics system. So occasionally, if you need to continually monitor the EC, and then occasionally in the aquaponics systems, you'll need to bleed off some of the water. Even though you're getting rid of some of those nutrients and it seems counterproductive, you need to bleed off some of that water in order to keep the salt level manageable. So this is a picture of what excess salt damage looks like on a strawberry plant grown in a coconut core perlite mix, basically using hydroponics. And you can see the marginal chlorosis, the burning around the outside edge of the plant, and then the overall discoloration of the leaf and cupping that you get from that. So another common problem that you're going to see in your hydroponic system from a nutritional standpoint is nitrogen deficiency. So typically the cause is under fertilization. So either my injectors aren't working properly, or I'm watering with clear water, or I didn't mix up the fertilizer solution properly, or maybe I'm leaching too much in my nutrient solution. Symptoms for nitrogen deficiency are typically light green foliage. So nitrogen is what we call a mobile nutrient, right? So it can be mobilized within the plant, and the plant can move it around and use it where it needs it. And so you can see in this picture the geranium here growing in a sand culture system. The nitrogen deficiency shows up on the oldest leaves because the plant is taking the nitrogen out of that old leaf and moving it into these young leaves to keep the young leaves alive and active. So the best way to manage that is to measure and monitor EC as well. So if we measure and monitor the EC is a pretty good proxy. EC being electrical conductivity is a pretty good proxy for the amount of fertilizer that I have in my solution for my hydroponic system. And then identify the source of the problem and correct that source based on your monitoring. So a lot of times it means that your injector is not working properly, or maybe you mixed up a nutrient solution, or one of your students mixed up a nutrient solution incorrectly. We can also have too much nitrogen, so we can over fertilize. So if we over fertilize and have too little leaching, we're typically going to see dark green leaves, very succulent foliage, a lack of flowers, which can lead to obviously a lack of production of flowering crops. So if I'm dealing with tomatoes, I'm going to see a lack of production of my tomatoes because I don't have the flowers. And then the other thing that too much nitrogen gives you is a strong susceptibility to insects and diseases, right? Especially aphids. Aphids really like plants that have too much nitrogen in them, and they will seek those plants out, and they will infest those plants, and you'll have this massive population of aphids developing on that crop because it has a too much nitrogen. Other insects as well will also be attracted to plants with too much nitrogen. So measuring and monitoring the EC again is a good way to help to manage that in your hydroponic system. And then again, based on your EC measurements, identify the source and correct that. And so you can see in this tomato picture where we have too much nitrogen, we've got the thick, heavy leaves and late blight being caused by the fungus Phytophthora. So in addition to insects, we can also cause increased disease susceptibility based on having our fertilizer solution out of balance. Calcium deficiency is, I would have to say, pretty rare in a hydroponic system in Pennsylvania because most of us are pumping water out of limestone aquifers from a well field. And there's usually a reasonable amount of calcium in that water supply. So for example, our water supply here in State College, PA, or on campus, the University Park, has about 40 to 50 parts per million of calcium in it before we do reverse osmosis and remove about half of it. So we end up with about 30 parts per million of calcium in our water supply. That's enough to grow most plants, but you do see issues sometimes based on the movement of that calcium. So we can see tip burn, blossom end rot, and other things like that. We'll see that fairly frequently, and actually we'll show you some examples of it on Saturday. We'll see it when we're growing in completely artificial light in a growth room, when we're using LED lighting systems, more commonly than if we're using HID or growing lettuce in the greenhouse. And the reason we see that tip burn under the LED systems, like I said, we'll look at this on Saturday, but it's typically because the LED grown plants are much shorter and smaller, and more tightly compact, thicker leaves, and the transpiration stream is just not strong enough to move enough calcium into the tip of that growing point. And so we'll see that tip burn and or blossom end rot. So detect that using media or plant analysis, sending samples into the ag laboratories here on campus, or any other plant analysis laboratory. This is the way you're going to detect that, and then we're going to cure that based on applying fertilizers and managing the air movement. So I see we have something going on in the chat here. Let me see if I can pull this up. Okay, so yes, I'll make the PowerPoints accessible to everybody. Absolutely. Okay, so here's a few examples of calcium deficiencies or calcium problems in plants. So the tip burn in lettuce, and we'll see some of this for sure on Saturday, happens because we're not getting enough calcium moving to that tip. Also, we'll see blossom end rot in tomatoes. Sometimes we can also see it in pepper. So we get blossom end rot in pepper, and secondary development of molds and other issues related to that come about because of the lack of calcium present within those systems. So another real common deficiency problem that we see in Pennsylvania, especially because of our limestone aquifers, is iron deficiency. And you'll definitely see it also if you're doing an aquaponics system and you're relying on the fish to provide the fish waste to provide most of your nutrients, because there's just not enough iron in the fish food and in the fish waste to provide enough iron to grow your plants. So it can also be caused by high media pH, nutrient imbalance, and then iron inefficient plants sometimes as well. So symptoms include intravenous chlorosis. So you can see that really strongly here in this petunia. This petunia was grown in a sand culture system. And you can see that the veins stay green, but the rest of the tissue kind of turns yellow and or white. And that's very common for iron deficiency. You'll also, if you get it really bad, so in this case, it's obviously a very bad deficiency symptom. The tips of the plant will actually turn white, and eventually they'll die. So detection by media or plant analysis, and then cure the problem by correcting the pH and or applying fertilizers to make that happen. So here's some iron deficiency on hydroponic tomatoes. You can see the intravenous chlorosis. We've got some yellowing of the leaves with a green midrib or green veins. Here's on the right-hand side is some of the hydroponic basil that we've grown in class with our students in the past in the aquaponics system. This is an interesting photo because you can see how yellow those lower leaves are up to a point, and then suddenly they start turning green. That's because we had the students add iron to the system at that point. So I mean, it's pretty dramatic how quickly a plant will recover from that when you add extra iron to it. So the new growth on that basil is just fine, but the old growth is just seriously messed up here. You can see how bad it is on all these other basil plants as well. So you can also have iron toxicity. Iron toxicity can be caused by low immediate pH, high iron in some acid fertilizers, or if I am using a high iron fertilizer and I'm watering with surface water. So we mentioned that iron deficiency is real common in PA. That's if you're watering with well water. If your water source is a surface water source, it's not uncommon for it to be fairly acidic. And then you're going to push that into the other extreme of the spectrum, where instead of a deficiency, I'm likely to see a toxicity problem. So the toxicity usually shows up as leaf spotting or marginal necrosis, stunting of the plants. And the way we detect that is by doing media or plant analysis, correct the pH problem, and or switch fertilizers if you have a fertilizer issue. Magnesium deficiency can be caused by high media pH, nutrient imbalance, low magnesium if you're not using dolomitic lime in your soilless culture system, or if we don't put enough magnesium in our nutrient stock solutions. Magnesium deficiency is a semi-mobile nutrient, so it's not immobile like iron. So iron shows up in the youngest tissue, typically. Magnesium deficiency often shows up in the middle part of the plant. You're going to see this kind of, again, sort of intervenal chlorosis, where you have chlorotic spots showing up in between the veins, and the veins are going to remain green. So lower to middle leaves, media or plant analysis will help you to detect that and figure out what's going on. And then we're going to correct the pH and or apply fertilizers to fix that. So it's not uncommon actually to see a magnesium deficiency. Boron toxicity can happen. Occasionally you might even see a boron deficiency, but it's more likely, depending on where you are in Pennsylvania, that you might see a boron toxicity. Normally you're going to see this occur where you have boron in your water supply. So there are some places in Pennsylvania where there might be as much as a part per million or so of boron in the water supply as background boron. And if I then add a commercial grade fertilizer to my hydroponic solution that has a lot of boron in it, I can see toxicity problems. So we want to remove that excess boron from the water supply and or switch fertilizers to something that doesn't have too much boron in it. So here's an example of boron in tomato leaves and what the toxicity looks like. So it's going to show up as a marginal necrosis and necrotic spotting of the plant tissue in a tomato. We can also see manganese toxicity. So manganese toxicity usually occurs with low pH. With high manganese, with high iron, sometimes we can actually induce a deficiency. And then with reduced conditions, we'll also sometimes see that. So it usually shows up as necrotic or chlorotic spots between leaf veins, dark green leaves. We have seen this occasionally in our operation with our students in the greenhouse. Normally it's in the gravel culture system. And when we're not adding enough manganese, we'll see manganese deficiency rather than toxicity. So correct the pH and correct the imbalance. Are there any questions about what we've talked about so far? So do you want to take like a 5 or 10 minute break for bathroom and whatever? And then Elsie can take over?
Sounds good to me.
Yep, I'm going to pause the recording and then we'll come back here in just a few minutes. It looks like we're recording. So welcome back, everybody, after our short little break. We're going to move forward with Dr. Sanchez talking about irrigation and water quality.
Thank you. So I'm going to talk about irrigation water quality, and I just wanted to just briefly let you know who I am, because just because I'm up here and you might wonder that. Anyway, I work at Penn State and I'm a vegetable specialist. And Rob and I started co-teaching a hydroponics and aquaponics course here for undergraduate students. Rob, was that like about 5 years ago? Does that sound about right to you?
At least 5 years ago. I
Yeah.
think. Yeah.
We've been teaching it every semester and it seems to be a pretty popular course. And so we're really excited to be sharing some of the information with you. And then on Saturday, we'll get to see several different hydroponic systems. We have a couple of aquaponic systems too. The students have been maintaining them all semester. So you'll get to see mature plants. There are some plants that are at younger stages too. So I'm hoping it will be a good experience for you. I know that we've put especially Rob has put a lot of time into thinking about making it a really hands-on and really information that you can use when you go back to your schools. If you need to get in contact with me again after, please feel free to do that. Probably the easiest way is by my email, which is ess11@psu.edu. And Rob's is, correct me if I'm wrong, Rob, rdb4@psu.edu. Yay. And either one of us would be happy to communicate, like talk things through, troubleshoot, whatever kind of issues that you run into. But today I'm going to talk about irrigation water quality. Irrigation water quality is something that really should not be overlooked. It's critical, especially in hydroponic systems, because large amounts of water are needed to produce crops. And the water quality is going to vary from location to location, and it really is dependent on the source and in some cases how that water is treated. It's the large quantity of water can supply unknown elements, and especially it depends on how you define hydroponics. And actually, maybe I should back up and do that. So there's two ways to define hydroponics. One way is like a purist kind of way where it's growing plants in water. A more broad definition of hydroponics is growing plants without soil. So if you're growing plants, for example, in soilless media, that would be considered a hydroponic system. Rob and I generally use the broader definition for hydroponics, but just to get us all on the same page with that. So especially when you're using a true hydroponic system, that's the only place that the plants are getting nutrients from. And so it's really critical that water quality be really high. Testing water quality is essential before you start and then during the growing season. It's really important to fine-tune nutrient management plans, also to work out if you have an issue with your plants. We always test water and do tissue testing as well. So water testing is a critical piece. Sorry, that's my dog. No matter how clean water looks, consider having it tested. And so there are certain things that we're looking for. We look at pH, the alkalinity, the hardness. Rob was mentioning SAR. We also look at the nutrient levels. And so I'm going to kind of talk about each of those and how we use that in hydroponic systems. As far as testing facilities, there are several labs that will test your water. They usually have kits. This is the kit from the Penn State lab. The kit will give you instructions about how to take the sample, as well as a container for putting the water in. We're really familiar with the lab here at Penn State, which is Agricultural Analytical Services Laboratory, which is available to you too. And we usually get the complete package, which I believe costs $55. Does that sound right to you, Rob? I think that's
about right.
Yeah, that's how much it was last time I checked. Anyway, it's important to use the kits because they need a particular amount of water in order to test everything in it. So once you send in your water sample, the facility will do the test, and then you will receive a report. This is a report that is from Ag Analytical Services, and so you can use different labs. One of the really nice things about the Penn State lab, however, is when you get your report back, they kind of provide an interpretation, and that can be really critical. It just makes it easier. So we have the analytes, your results, the units, those results come in, and then again, a little bit of information to help you interpret the result that you got. So now I'm going to go through some of the different components that are analyzed and talk about how they relate to hydroponics. So as Rob mentioned earlier, SAR is a sodium adsorption ratio, and it's a measure of the dominance of sodium relative to calcium and magnesium. It's a really critical thing to look at in a water report. If you have a high SAR level, that can cause root damage to your plants. And just again, note that the amount of sodium that's a problem, it depends on those other items as well. So the amounts of calcium and magnesium. If you have a high SAR level, often you need another water source. One of the hardest things for me is being an extension and working with commercial farmers is seeing these reports. And sometimes you do have to tell a farmer, unfortunately, you need another water source, because there are ways that you can treat it. However, it's usually reverse osmosis, which can be expensive, especially in a small scale. You can also dilute water that has high SAR values, if it's not too high, with rainwater. And we'll see some farmers do that, like they'll capture rainwater in some sort of a tank and then add that to their irrigation water. So the values that are critical for that is you don't want it above 2 if you're using for this interpretation. So in this case, the one we have here is 2.73, so that one is too high. pH, Rob talked about pH a little bit. That's also one of the first things that I zero in on when I look at those reports. As he mentioned, it's an intensity measure. It expresses the activity of the hydrogen ions. And it's the pH that we generally talk about for most plants. We talk about it in terms of soil, right? So for soil pH, we often say, we want it between 6 and 7. However, for hydroponics, we go a little bit more acidic, and ideally for most crops, we would like the water pH to be between 5.5 and 6.5. So the importance of pH, Rob showed about nutrient availability, and the redox state, he mentioned the importance of that, and determining the form of the nutrient that's available and how critical that is for nutrient uptake. And so here's just an example with phosphorus, and Rob kind of talked about this too. And this is just showing the different forms that phosphorus takes depending on the pH. So when the pH is less than 2, the form is phosphoric acid. If it's 5, it's dihydrogen phosphate. Around 10, you get into hydrogen phosphate, and then above 14, it's phosphate. And so the form that's most available to plant is right here with your pH 5 and your dihydrogen phosphate. So that's why it's really critical to look at that level on the soil test report. And oftentimes we will recommend adjusting pH if it's out of the optimal range. But it's important not to just look at the pH by itself. You also need to consider the alkalinity of the water as well. Alkalinity, as Rob mentioned, is a capacity measure, and it measures the capacity of the water to neutralize acid. And so when we look at the alkalinity level on a soil test report like we have here, it's going to be expressed in carbonate. So we've got the carbonate here, and then we also have the bicarbonate as well. And so, that's just a common way to express that. So the alkalinity units are parts per million, or milligrams per liter. Those two things are equal. And Saturday, when we look at nutrient calculations, that conversion, that being equal parts per million to milligrams per liter, those things, we will be using that over and over again. So I wanted to show you an example about why it's important to look at alkalinity and pH together. And so I'm going to just show you 2 examples of water. And so here we have an example where the pH of the water is 9 and the alkalinity is 25 parts per million, or milligrams per liter. And so in this case, 1 drop of acid can change the solution pH to 6.0. So if that's what we're going for, it's 6.0. So it changes relatively easily. Now, on the second example, the same pH 9, but this time the alkalinity is much higher. And so again, if we want to change the pH to 6, just for this example, it's going to take 10 drops of acid to change that water solution. So that relationship between alkalinity is really important because it helps to tell you what you need to add or how much of an acid you need to add to adjust the pH, bring it down if you're going to bring it down. So this is just another figure, and it kind of shows that relationship too. And so here we've got some water, like a pond water, for example. And what we're doing here is we're looking at pH and alkalinity, and with this bar right here being low alkalinity water, and then this bar right here, this line right here being a higher alkalinity water. And so we're looking at pH from 5 to 11, and then at different times of the day. So the early morning, mid-afternoon, and then early morning. So we're going through an entire day here. And so you can see the high alkalinity water, it pretty much keeps the same pH throughout the day. But if we look at the low alkalinity water in the early morning, the pH is lower than in the day where it reaches its peak, and then it's low again in the early morning. And so this water again is not very buffered. And so what happens is during the night when the plants are respiring, the roots release carbon dioxide, which acts as an acid in the water, and that decreases the pH. But in the daytime, the plants photosynthesizing, and that's not happening. And so the pH goes up. And so that's why it's really, really important to look at pH and alkalinity again together. This is just showing a couple of irrigation water tests. This is from a farmer here in Pennsylvania, and he had a pond, and this is the exact same water source, and he just took his samples at different time of the day. And you can see the pH at one time of the day was 8 and was 9 at a different time of the day. And it's important to remember that pH is on a logarithmic scale. So even though the number, you're like, oh, that's just 1 unit, that's actually a 10-fold difference. So the difference between 8 and 10, for example, is a 100-fold difference. So that's actually a pretty large difference in pH going from 8 to 9. So when the water pH is too high, what we generally recommend is acid injection. And there are a few acids that are commonly used: sulfuric, phosphoric, and nitric acid, and citric acid. And we've also seen a little bit of vinegar being used. There's a commercial farm that Rob and I used to take the students in our class to, and they used vinegar as their acid in that particular case. We don't go there anymore because they switched to cannabis production, and they were growing tomatoes, but I'm guessing they're doing something similar. So things to consider: if you are using the organic methods, if you're doing like certified organic hydroponics, then sulfuric, phosphoric, and nitric acid aren't allowable in organic systems. So you can use the citric acid or also vinegar. That would work too. The other thing to consider is phosphoric and nitric acid are adding phosphorus and nitrogen as well. And so you would need to consider that in when you're putting together your nutrient solutions. The most common source that we see use is sulfuric acid, and it's because it's the most readily available. Farmers will go buy battery acid and use that to adjust the pH of their nutrient solutions. There is a really cool tool online. It's out of the University of New Hampshire that's called the ALK Calc. There's the link there, but you can also find it pretty easily with a Google search of ALK Calc. And it's really nice tool because what it does is you plug in some information. So the pH of your sample, the alkalinity of your sample, and then where you would like the pH to go. You tell it what kind of acid that you want. And this only works for the sulfuric, nitric, and phosphoric acids. But then it will spit out a report that tells you how much of that, in this case, sulfuric acid, to add based on all those parameters that you set. So in the case of using citric acid, there's a nice publication out of North Carolina State University, and it goes through nitric, phosphoric, and sulfuric acid, but it also goes through citric acid. And so you can use this table right here, which I just blew up in this next slide, to determine how much citric acid to use if that's the acid that you are using. This is that basil plant that Rob showed you. And I put this in here just to remind me to let you know, we have water that has high pH in our system. It's like a little over 7.3 or so, Rob. Does that sound about right?
It usually runs more like 7.5.
7.5. We don't adjust it. Our reasoning behind that is because we work with a lot of students. There's a lot of people that are in the greenhouses when we're not in the greenhouses. And so we just decided that we really didn't want to deal with the acid. And so we see, I guess the biggest consequence of doing that is that iron deficiency that Rob was showing you with this basil plant. And so we tend to add we tend to see a lot of iron deficiency symptoms, and we tend to add a lot of nitrogen to our systems. So just something to keep in mind. One of our extension educators, I was talking to him, and he was saying that most of the farmers that he knows that use acid injection have some sort of, an acid, or have gotten some sort of an acid burn. So we just don't want to deal with that. Okay, so that's pH and alkalinity. Another thing to look at on those reports is hardness. Hardness is different than alkalinity. It's a combined measure of the carbonates and the non-carbonates. So it's kind of the carbonates plus. And so carbonate hardness can be treated with acid. So if you have hard water and it's primarily carbonates that are causing the water to be hard, then that acid injection will also help with that. Non-carbonate hardness won't. So when you have a high hardness value, it's not really going to be an issue from the plant perspective, but it can be an issue in the pipes. If you're using like a drip irrigation system also, for example, it can clog the emitters. And we actually see a lot of this. We have in our NFT system, which you'll get to see on Saturday, we have these really small spaghetti tubing that feeds the gutters, and they're always clogged. I'm exaggerating. They're not always clogged, but they're often clogged, and students weekly go through and unclog those. It can also, hard water can decrease the effectiveness of some pesticides as well. So here's just an interpretation of hardness. Just if you're wondering, like I grew up in southern New Mexico, and everyone used to always say, we have really hard water, and I never really knew what that meant. Well, now I do. It means that in parts per million, the water hardness was somewhere between 201 and 300 parts per million. So this is just an interpretation of that. Salinity is another important thing to look at on the irrigation water report. As Rob mentioned earlier, salinity is the total amount of dissolved salts in the water, and it's usually measured in as the EC or the electrical conductivity of the solution. And we will actually be doing, as Rob said, a lot of EC measurements on Saturday. So having an EC meter is a really important tool for hydroponic and aquaponic production. So conductivity increases with salinity, and then the units are either millisiemens or millimoles. And Rob showed some great pictures of elevated salts, but I've got a couple too. So this is just where you're showing that marginal kind of necrosis. This is the same thing. This is salt damage on lettuce, and here is salts damage on a coleus plant. So when the if the salt levels are higher in the water or the media, so if you're using a hydroponic system where you have some sort of a potting soil, then what happens is that water can actually, the direction of water flow is wrong, right? It's the water, instead of moving from the soil to the plant, is going to move the opposite direction. And so you have what's called a chemical induced drought. And so we don't see a lot of issues with this so much with our water-based systems, but we haven't seen it with the students either in our media-based systems, but we have seen this quite a bit in high tunnels. That's one system where this has become a problem.
Yeah, we've seen it with the tomatoes where we don't change the reservoir solution frequently. And so if we let the reservoir just get refilled over and over and over again from the stock tanks, and then eventually we end up with salt problems. What was it? We ran up to like almost 5 one time, didn't we?
Right, that was recently. And actually, they'll get to see the effects on the leaves from
yeah,
the lower
exactly.
leaves. And then the other thing to think about is the nutrient levels that are in that water report. And this is really important in hydroponic and aquaponic systems, because we will use the nutrient levels that are in that report to adjust the nutrients in our recipes. So for example, if you're doing a hydroponic system, there are 3 main approaches to building a nutrient solution. You can use a complete fertilizer, and I'll talk about that in a second. You can use a company or fertilizer program, and I'll show you that, or you can use a recipe. And so going through those 3 ways of approaching it, this is an example of a complete fertilizer. So this is from a commercial farm in Pennsylvania. And within this trash can, it's got, see 20, 10, 20. So they just have a complete fertilizer. I'm like almost 100% positive it's a complete fertilizer plus micronutrients that they're using for that. And they just mixed up a concentrated solution of that. And you can see that the dosatron, the fertilizer injector, is just taking up the nutrient solution from that trash can. This one is just in the picture. I think they go back and forth depending on what they're growing between these 2 solutions. At this time, they're using this 20, 10, 20. And that's how, in this case, they were providing nutrients to a lettuce crop. So that's one approach. And there are some advantages and disadvantages, as you would expect, from that approach. And so it's, of the 3 methods that I mentioned, it's the easiest. You just need 1 bag of fertilizer. You only need 1 fertilizer injector. With both other ways, more commonly use 2 or even 3 fertilizer injectors. And you're using fertilizers that are really commonly available. You can find them really easily commercially. There are disadvantages too, though. They may not provide the proper balance of nutrients to the plant. So it's kind of a generic way to approach nutrients solutions, and you're not really getting specific to different types of plants. I mean, I guess you can adjust a little bit the nitrogen, or phosphorus, whatever you're going to zero in on, but it's just not as exact as some of the other methods. And they may not provide adequate amounts of nutrients that are not in the fertilizer as well. Like I mentioned, we don't adjust our soil pH. I would expect we would have some issues with iron with one of these going this approach. And although we do this approach, you will see all 3 of these approaches when you come out on Saturday. So the second approach is to use a fertilizer or a company program. So this Hydro Gardens fertilizer, this is from Hydro Gardens. This happens to be a tomato formula, but we use this for our cucumbers. We have a cucumber formula that we buy too. So it's a different bag. The reason I know this is tomatoes is because all the text is in red. The one we bought is cucumbers and all the text is in green. But they have some sort of a complete fertilizer. So this one is a 4-18-38. And then on the back of the bag, they have directions for how to use that fertilizer. So here's this fertilizer for 1338 tomato formula, and to make 100 gallons of plant nutrient solution. So this is normal strength. We're not concentrated strength at all. And then you have the 2 stages to choose from. Are you at the seedling stage, or are you at the mature plant stage? And then it tells you how much of this fertilizer. And generally you have to add calcium nitrate, maybe some potassium nitrate, depending on the program. And in this case, also magnesium sulfate. And then it also tells you what to adjust your pH to. So that's another way to do it. You use a program. So again, you get the fertilizer from the company, and then you add a few other things. So some advantages to this is they're also pretty easy to use. Minimal ordering of fertilizers. You saw in that particular example, you needed the fertilizer from the company and then 2 other fertilizers. There's very little or even no mathematical calculations. If I was going to do a normal strength 100 gallons of that, I would just have to weigh out exactly what was on the bag. But there are some disadvantages. There's no easy adjustments of individual nutrients. If I do a tissue test and it tells me I don't have enough phosphorus, there's not a really easy way to adjust the phosphorus level in that in this system, as an example. And you also can't adjust for nutrients in the water source. So we just looked at that irrigation report, and it told me, I'm going to go back, I'll go slow so that it doesn't make your eyes go weird. But it told me like that I have that's not a lot. Let's use calcium. I have 29.18 milligrams per liter or parts per million of calcium. I don't have any way with a program to say, okay, I can just add, 29 less milligrams per liter of that fertilizer to, in the solution. There's no way to do that. And so that is a disadvantage of these programs. And they can also cost more than using recipes. Like I said, we do this, and you'll see this on Saturday. We have this for our cucumbers that we're growing. The last way is to use a recipe. And there are lots of recipes out there, one that we commonly use and one that you will get to use and build or make a solution with on Saturday is the modified Sonneveld solution. And so it's like this. It tells you, okay, in your solution, you want 150 parts per million of nitrogen, 31 parts per million of phosphorus, 210 parts per million of potassium, 90 parts per million calcium. Now, I hope you can see right away, if I know that I have 29 parts per million of calcium in the water, I can subtract that from this. So if my recipe needs 90 parts per million, I can subtract 29, and I can just add 61 more parts per million. So you can start to use your fertilizers more efficiently if you have a fertilizer solution. So looking at some of the advantages and the disadvantages, you can adjust all the fertilizers. And so there's kind of another example. So if you have a recipe that calls for 210 parts per million of potassium and your water already has 30 parts per million, you can reduce that 210 when you're making up your recipe. It's easy to adjust the nutrient levels. I mean, you just do that quick subtraction and then go from there. So because of that, you can use fertilizers more efficiently than in the other 2 methods. And it can be less costly, especially compared to the fertilizer programs. Some of the drawbacks are that calculations are needed. We are going to show you how to do the calculation on Saturday. And so Rob's going to go through and show you how. And then we have this really neat activity where you'll get to do the calculations and make up a solution. And we're going to build a standard curve. So the calculation is something that you can become really familiar with. In our experience, sometimes the students in our classes get a little intimidated because there's math involved. So we usually start off with some sort of a pet talk, it's just division, it's just multiplication, a little bit of subtraction, a little bit of addition, and these are all things that you already know how to do. So we'll show you how to set that up on Saturday. And especially with the micronutrients, you might need a scale that can measure small amounts pretty accurately, because we do use small amounts of the micronutrients. So that's, hydroponics system, and in aquaponics systems, it's pretty much the same. So this is an aquaponics system. This is when Rob and I went to Saul High School in Philadelphia. I liked their system because of the little window that they had in their fish tank to see their tilapia. But what we found is that in our systems, this is actually two systems. So this fish tank here is feeding these two beds back here. And then this fish tank here is supporting these two beds right here. And what we found in our systems is that the fish don't provide enough nutrients. And so what we'll do is we'll take a water test and we will amend the system in order to provide enough nutrients so that we get nice crops out of our aquaponics system. And so this is a water test that it's from our aquaponics system. And so what we'll do is we'll take that same modified Sonnefeld solution recipe that I just showed you a minute ago, and we'll do the same thing where we'll, subtract the amount of nutrients that is already in the water, and then we'll get the rest of the nutrients. And then how we add it, I know there was a question about that earlier, well, two things. One is we avoid using ammonia when we are building our, when we're getting our fertilizers together to add to the aquaponics system, because it's toxic to the fish. So that's one important thing. And then the other thing that we do, this is that same picture, is so in our system, the water first comes into this end of the bed, and then it flows all the way down here, and then it goes back out into the fish tank. And so we will add the nutrients at the beginning of the plant part of the aquaponics system. And then it moves through the fish tank or through our deep water float bed, and then it goes back into the aquaponics system. Another thing you could do is add the nutrients to the biological filter. And some folks do use ammonium even in their aquaponics system. We haven't done it. The biological system should take care of it, but we're like, let's just not risk that. But that's another way that you could add nutrients to your aquaponics system. I know someone had asked about that. So that's all I wanted to say about that. I'm pulling up the chat right now.
I was going to say, there is a question in the chat there for you. I didn't want to interrupt you as you were going.
So let's see, it says, is there a rule of thumb for how frequently to change the stock solution in the reservoir? Okay, so it depends on your system. So for NFT systems, those are changed out about every 2 weeks or so. Usually, obviously in the aquaponics system, we don't change it. Sometimes we bleed the water though, if we feel like the nutrient solution, the EC gets too high. For our deep water float system, we don't usually change that out because usually we need to remake the solution and we lose it through evapotranspiration before it ever becomes a problem. Rob, am I forgetting any other systems out there? Oh, we have a Beto bucket system.
Yeah, and that one we have to change out fairly frequently in order to not have the EC get too high. And we have had that EC get way too high in that one. Usually that happens over the summer months when we don't have anybody taking care of the system pretty much. And so it just gets refilled and refilled and refilled. And eventually the EC gets pretty high. Commercially, most people in a commercial setting will change out stock solutions or the reservoirs about once every 2 weeks or so, or at the very least in between each cropping cycle.
Hey, are there any other questions for Dr. Berghage or Dr. Sanchez? You're welcome to unmute yourself. Okay, well, I'm really excited for this weekend. And I know the other teachers are too. So thank you guys so much for giving us this good overview of everything. And we're trying with the style a little bit to get seeing how it works for us with doing a little bit of content ahead of time. And so we're a little bit more prepared when we come into these workshops. So folks, before we log off for the evening, please join me in thanking Dr. Sanchez and Dr. Berghage for being with us tonight. And as well as I do want to go over a couple of points in John's email just to make sure that everybody is on the same page and I can answer any questions that you might have. I'm going to keep this recording because like I said, we do have a few folks that couldn't be on tonight in case there's anything that comes up that might be helpful to them. So as I pull up John's email here, so the first thing I want to just kind of draw your attention to is in that email, there was a link to the agenda. So if you have any questions about things that we're covering or what time we need to be where, that agenda is great for that. Couple of things, the new and beginning piece, a lot of you are in the new and beginning program. For those of you who aren't, just a quick overview, we've decided to bring both or to incorporate this as part of the new and beginning teacher program. And so we are meeting at 4:30 in the classroom in Head House 1. There's a map on John's email that he sent out. Park in the creamery deck, like he mentioned. I'll give you guys a parking pass when it's time for you to leave, and that'll get you out of the parking deck. So when you come in, just take the ticket and keep and find yourself a good parking spot. Come out there by the creamery, across the street. You're right there by the head houses, and come to the closest one to the corner of Curtin and Shortledge, and we'll be right inside the door. There is the classroom. So with that, if you are new and beginning, again, 4:30, we'll have Dr. Susanna Wyndham talking about community engagement. That'll go from 4:30 to 5:30, and between 5:30 and 6, we welcome any of the other participants to come in and join us as well. John and I'll be setting up some dinner. For those of you who are with us in the summer and Chipotle kind of fell through on us, we decided to go with Qdoba this time. But as promised, we will be doing some Tex-Mex, I guess. And once we've had a chance to eat and socialize for a little bit, we're going to dive back into the hydroponics and aquaponics with Dr. Berghage and Dr. Sanchez. Or actually, no, I think we're doing high tunnels. Sorry, my bad, high tunnels. And then from there, you guys, once we're done with those conversations, again, we'll give you the parking passes, head out. You're staying at Toff Trees. I know some of us were pretty used to staying at the Wyndham, but there's a event going on this weekend for one of the sports teams. So they were all booked up. So don't automatically drive to the Wyndham, drive to Toff Trees. And you'll be staying there for the night. And then in the morning, we're going to be in the same spot. We'll give you a parking pass to get back into the creamery. And we'll have some light breakfast, bagels, pastries, a little bit of fruit, coffee to get us going on Saturday morning. And also in the email for lunch, we're ordering from CC Peppers. We're really trying to support some of the local businesses in town. And please check out that lunch offering. And John has a Google form there in the email to submit your lunch order. Please note that he wants that done by Thursday at 5 p.m. That way we have time to organize the order and get it over to CC Peppers so we can have everything done in a timely manner. And Dr. Berghage and Dr. Sanchez, if you haven't done so already, that includes you as well. So please make your lunch selections. And I think that should cover everything. For those of you who haven't joined us before, dress is casual. So jeans are fine, khakis and polo are fine as well.
And in fact, actually, we're out in the greenhouse, so I would encourage you to wear jeans. You really don't want to wear nice clothes when you're working in the greenhouse.
Yeah. Dr. Berghage is, I'm assuming, kind of warm in there too. So maybe layers, t-shirt and a sweatshirt.
Yeah, layers would not be bad, although this time of year it's not so terrible. Yeah. So if you have a pH in EC meter of your own, you might want to bring it to use it. We have a couple of them that we use with our students that we're going to be using, but a few extra ones wouldn't hurt, and we can always check the calibration on them for you and that kind of thing. In the emails that went out, the Penn State mask mandate was explained. We'll have some extra masks around in case anybody needs them. So we always keep a supply, because students show up all the time. They've forgotten their masks. So we keep a supply of them in the head house. So we're good to go with that. And then in the email, it also mentioned that if you have a like a 1 gallon milk jug or soda bottle or something like that, and you want to be able to take some of the, so we're going to be mixing up a modified Sonnefeld solution. You're going to be planting some microgreen seedlings. If you want to take some of that solution that you make up home with you to water your microgreen seedlings, bring some kind of a container to put it in.
I also wanted to just say, I think I'm speaking on behalf of Rob too. You can just call us Elsa and Rob.
Yes, please.
Great. Actually, I was going to ask you for the clarification on the water bottle. So I'm so glad, or the gallon bottle. So I'm glad you guys mentioned that. And is there any questions out there regarding tonight's presentation or the weekend plans? Okay, so if not, I'm going to stop the record button. Here we go.